Own instance architecture. I'll talk about what this term actually means. It's not actually, a well-defined term. It's not a term that's actually out there. It's just a small phrase I've come up with to describe the problem statement that I'll be talking about. I'll be talking about what that problem statement actually is, how it's solved, the naive way of solving it, the better way of solving it, and a bunch of applications that a lot of people around the world have used today actually end up using the problem statement that I'll be talking about, and how the solution that I would talk about is somewhat in some version what a bunch of these companies end up using. And and yeah, so I'll dive right in. Cool. Before I go on to use cases and the why, I'll just quickly talk about what the problem statement actually is. So an application called Replit, or let's say Code Sandbox, these are a couple of applications, websites, whatever you want to call them, which essentially allow you to create your own code bases, so to speak, in the browser itself. What does that mean? That essentially means that if I go onto these websites and if I say create new, I don't know, Java project or Node.js project, or anything basically, or Go project, whatever it is, it would provision a bunch of resources, hardware compute resources, or a machine somewhere in the cloud for you, and that part of the machine essentially belongs to you, and all the files that you edit, all basically everything that you edit would get edited on the actual VM that is provisioned somewhere. So any file that you edit, let's say you create a new file called utils.ts, which is a TypeScript file, for instance, in some TypeScript project that you created in the browser. So whenever you actually edit the file, this file would be actually be edited on the file system on that VM that exists somewhere in the cloud. And let's say you have another project, right? Let's say a Go project. You create a new project on the website, and you provision, let's say, a main.go file. When you're actually writing, let's say, the main function, everything that you're editing is actually going to a file system that exists somewhere on the VM in the cloud, essentially. And this sort of whole slides deck or whatever is essentially to talk about how you actually solve this problem, how you provision resources, and some of like the interesting problems around, let's say I have two different projects. Let's say I have one, TypeScript project and one Go project. And let's say the TypeScript project is running extremely compute heavy stuff. Basically, it's not, let's say it's just, running a bunch of Go routines which are extremely compute heavy. Basically, it's, I don't know, it's running something that's extremely compute heavy. And let's say you have another TypeScript project which is doing something extremely lightweight. You'd want this architecture to be multi-tenant in the sense that the resources that are getting utilized here, let's say this is assigned, let's say 1 GB of RAM, and this is assigned, let's say 1 GB of RAM. You don't want the high compute being used on this machine to actually affect the resources on this machine, if that makes sense. And that essentially, talks about the use cases and the why and the problem statement, where I want to be able to develop a system such that whenever I click something on the UI, I provision resources in the cloud that I can access from the browser, a file system that is getting edited from, let's say, the application server that gets access to that machine that is running somewhere in the cloud. And this architecture needs to be multi-tenant in the sense that the resources that are used, which may be heavily used on one, let's say, VM, so to speak, need not affect how the other VM or how the other thing that we've provisioned in the cloud is actually performing. And these are a couple of problem statements to talk about, and essentially a use case. So Replit and Code Sandboxes are the most popular example for this. And I'm sure there's a bunch of other applications that also use sort of this high level architecture of wanting to provision instances on demand and being able to access those instances from application servers, and you being able to, from the UI, hit the application server does something in the file system on that VM, and eventually returns back a response through that entire architecture. Cool. So the bad architecture. Now, the bad architecture, this is just called bad because it's an architecture that doesn't work, but this is also the first thing that came to my mind when I was coming across this problem statement, looking at a bunch of random videos, blogs, whatever, and but it's bad nonetheless. And I'll go over what that architecture actually is. So when we say, spin up your own instance with your own computing resources and your own memory, whatever, the first thing that comes to mind possibly is just spinning up an EC2 instance in AWS. What does that mean? That basically means that I, for every user who creates a new instance, I just spin up a new EC2 instance, and this solves the initial problem of having separate memory, separate RAM, separate compute resources. And let's say I first spin up a Go project that spins up one EC2 instance. I then spin up, let's say, a TypeScript project that spins up a second EC2 instance. What that basically does is that I now have memory, RAM, compute, whatever, CPU, all of those resources allocated on this EC2 instance separately and this EC2 instance separately. And why that's good is because now I don't have any shared compute. I have separate resources per instance, which is actually a problem we wanted to solve. And using EC2 instances actually solves that initial problem. And the other problem about making sure the multi-tenancy where one load doesn't affect the other, it doesn't in this case, because if I have one EC2 instance that, let's say, has 1 GB of RAM, and I have another EC2 instance that, let's say, has 1 GB of RAM, if I use 900 megabytes on this first instance, it actually wouldn't affect anything on the second EC2 instance because they're actually two independent resources running separately somewhere in the cloud. And this solves that problem. But there is a whole domino effect of other problems that actually come in with this potential architecture. Firstly, DNS resolution. So if you've ever tried to create an EC2 instance and try and run like a basic thing on an EC2 instance, let's say like a simple Node.js server, for instance, there are a couple of things that you need to do in that process if you're doing this process extremely naively. So you, one, spin up the EC2 instance. Two, you actually, after spinning up the EC2 instance, install Node, do all of that, and that's all fine. And then let's say you start running your Node.js web server, for instance. To be able to actually hit this Node.js web server, one of the things that is slightly tricky is that this web server firstly would be running on HTTP and not HTTPS, which means that you actually need to figure out and install a certificate on this web server, and only once that is done can you hit the web server on HTTPS. And the other thing is that each EC2 instance has its own unique URL that is associated with it. And what you would be doing essentially is hitting that specific URL associated with that EC2 instance. Um, Now, what does that mean in terms of our architecture? Well, there's two problems. One, we earlier talked about how if I'm spinning up my own instance, I would want it to have, let's say, my main.go file, which is actually what I'm editing from the UI. It needs to exist on the actual file system. And I want my application server to actually have access to this EC2 instance and to be able to run commands on it, possibly, let's say, or to be able to hit the EC2 instance, do whatever with it, basically, so that if I make edits to my main.go file, those edits actually go onto the EC2 instance's file system. But the issue with that is that the application server is actually going to be running on HTTPS. But this EC2 instance initially, when spun up, is going to be running on HTTP. After you install Node, you start running whatever, you start the EC2 instance is running whatever. Everything is running on HTTP. There's no certificate installed. There's none of that. None of that is going on basically. Therefore, it means that you possibly need to create certificates on the fly, and you need to create new records in, let's say, Namecheap or GoDaddy, which are DNS providers, on the fly. And that is a very dumb thing to do. And the reason it's a dumb thing to do is because DNS resolution takes hours. sometimes it can take a day, and this is, us being optimistic about it. Realistically, it takes, a few hours or so. But if you go on to Replit, and if you click on spin instance, or like start Java project, start, TypeScript project, it's not going to take hours. It'll take, let's say, 30 seconds, 1 minute at max, and then you eventually have your instance in front of you running, and you can start writing code, and it'll actually start editing the file system on the actual instance where you're running um, your resources. So this is an extremely big problem. This immediately creates a bottleneck, because you'll now have to wait for multiple hours before that instance can start running. You'll have to keep polling from your application server to see, hey, is DNS resolved? If it's not resolved, why is it not resolved? There's no real insight into it. So it's a bottleneck, right? And the one, naive thing that you can maybe think of, if you think about DNS resolution a little bit deeper, you can maybe think that, I can have wildcard domains. So basically, so let's say if I have a domain name called x.anish.com, that's a wildcard domain where x can be any value, and I can associate that x.anish.com to an IP address, but each EC2 instance has its own separate IP address because it's running somewhere else. And that's a problem, right? And therefore, you can't even do wildcard domains, which means you need to create DNS records on the fly, which is a big no-no. It'll take hours just for the EC2 instance to actually start running, spinning up, and also the problem is that spinning up an EC2 instance takes a certain amount of time, which is more than 30 seconds. If you've ever tried to spin up an EC2 instance, it would take more than 30 seconds, right? It's not going to take minutes, but it will take more than 30 seconds. It would take time to initialize, it would take time to start running, and then there'd be a separate overhead on actually time overhead to actually try and set up all the dependencies that need to be installed on this machine, and then you wait for DNS resolution. Too big a problem, right? And connection to each of these instances, which basically ties up with the DNS resolution problem, which is that if you don't have, firstly, like, you need to install certificates on the fly, and once you've installed certificates on the fly, which I don't even know if that's possible, but even if you get past that step, you need to actually create records in the DNS provider on the fly, given that Namecheap or GoDaddy provides an SDK or an API that you can actually hit to be able to do so. But that's a hard problem to solve, and it's not solved yet, and time heavy. The obvious thing we've talked about, where it would take hours for DNS resolution to actually happen. So this architecture becomes bad. It's a big no-no. No user wants to wait for hours to be able to start writing code on that Java project in the browser. So they would want something different, basically. And this is where a Kubernetes-based solution comes into the picture. What is Kubernetes? Kubernetes is basically this container orchestration tool which allows you to spin up a bunch of constructs like pods, services, ingresses, ingress controllers, and a bunch of other stuff, CRDs. What are these, and why they're useful in the context of Kubernetes, I'll get into. And what constructs does it have to solve for the DNS problem? So our main problem with the EC2 instances architecture is the fact that every EC2 instance is going to have its own IP address, which you obviously don't want to store in an application database to figure out which instance to hit. And also that it takes time to provision all of this, and to open new ports, you need to, again, figure out a way to create new security groups and do a bunch of all of that complicated stuff, which we want to avoid. And also that DNS resolution on the fly is a pain, because each EC2 instance has its own IP address, and it would take hours for DNS to resolve, and we don't have that much time. So how does Kubernetes solve this? So I'll talk about a bunch of the Kubernetes constructs that exist that actually help solve this problem. Cool. So firstly, we have pods. Pods are basically the most fundamental unit piece of Kubernetes. A pod is, think of a pod as this mini machine which you can allocate your own memory, your own RAM, your own set of resources to, and you can spin it up within your Kubernetes cluster. And you can create as many pods as you want. Kubernetes has the ability for, you can have more and more nodes in Kubernetes, and therefore you can have more and more pods. You, and basically pods are the single most fundamental unit in Kubernetes, which you can allocate resources to. And let's say if you have 1 GB of memory, let's say of 1 GB of RAM associated to a pod, if I use 900 MB here, it won't affect the functioning of the other one, of the other pod that, let's say, has 900 MB, let's say doesn't have 900 MB used on it, basically. So pods are the most fundamental unit here. And then you have services. I'll come to how all of these tie together in the application, but first I'll just talk about what each of these components actually are. Services are basically what give access to a pod. A pod in itself cannot be accessed from an external client like an application server. Like there is no real external IP, or there's none of that going on. You need a service which can give you access to a pod. And a service is designed to do exactly that, to give access to a pod externally. And each service has its own external IP, its own separate external IP that gives access to a specific pod. You then have an ingress. An ingress is designed to give access to a specific service. Now, why do we have this 3-tier layer? Like, why do we have an ingress if a service already gives us access to a pod? Is what I'll come to later. But service gives access to pod, ingress gives access to service. That's the most important part to understand here. We can forget the fact that these are, two different blobs, two different pieces here. But just if we just look at this one, we have a pod, service gives access to this pod, ingress gives access to the service, and an ingress also has its own IP and stuff like that. And ingress controller is also something that has, now the other thing to note here, by the way, is that each ingress has its own different IP, which means that it's similar to the EC2 instance thing, where each service has its own IP, each ingress has its own IP, and each of them, these are all separated units. So you can think of them as these three together. You can think of as, it's not the right example, but you can think of it as separate EC2 instances. So one EC2 instance, two EC2 instance. So this has its own, set of IP configurations and, the networking layer. And this also has its own separate networking layer in the sense that it has its own IP address. And so if you really try and connect the dots, this is one EC2 instance, this is two EC2 instance. So we still have that problem of, having to create DNS records on the fly, if that makes sense, because, we still don't know how to reach the pod. And that's where an ingress controller comes in. So an ingress controller is basically, in our case, the entry point of our application for how to reach the pod. But essentially, an ingress controller is something that monitors all ingresses. And an ingress controller only has a single IP. And it is this single IP that we would put into GoDaddy or Namecheap or any one of the other DNS providers, basically. And now let's come to what this translates into in the context of our application, and why this architecture, like what is the point of having an ingress controller which monitors all ingresses, and a set of ingresses have their own IP, services have their own IPs, and service gives access to a pod, ingress gives access to a service. What's the point of all of this, basically? Cool. So like I said, pods are the most fundamental most unit of Kubernetes, and this is actually where the file system would live. So let's say if I create a Go project or a Java project, let's say the main.java file or the main.go file is actually going to live on these pods itself. So theoretically, when I, let's say start Java project, you would spin up a pod, you would have a Docker image or basically something that would help you install a bunch of dependencies on this specific pod itself. So let's say if you have a Node project, then like a Node.js project, then install Node. If it's a TypeScript project, then install TypeScript. Do all of that stuff. And let's say if this is a Go project, then install Go on this specific pod. Allocate, using a YAML file, you would allocate a certain amount of RAM and resources to this specific, each of these pods, basically. And you would then spin up a service, and this service would actually give you access to this pod. So far, what we have is our file systems, which means that you have your main.go file here, you have your, let's say, main.ts TypeScript file here or whatever it is, and you have a service which has its own external IP which can give you access to this pod, which means that theoretically, if I can hit this IP, I can actually get access to the pod. But we don't know what that IP is yet. Like the application server doesn't know what that IP is, and we don't want to store that IP address in the database. But currently, we have that much set up. And you also spin up an ingress, and what an ingress is doing is giving access to a service. Why we also have this ingress, again, as I said, it's because of the ingress controller. This can essentially be thought of as a package for why we have it, but you spin up an ingress which gives you access to a service. Each ingress has its own IP address, its own thing, and essentially now this is one EC2 instance, this is a second EC2 instance from the analogy that we drew, right? We have a pod. The pod has its own file system. The pod is where you install all dependencies, you install TypeScript, you install Node. If it's a Java project, you install whatever you need to install. If it's a Go project, you install Go on the pod itself. You using your YAML configuration, you're also configuring all the memory and CPU requirements. You're also creating a service which gives you access to this pod, and you're creating an ingress which gives you access to this service. That is what we have so far. Now, the ingress controller monitors all ingresses. What does this mean? So a pod usually has a name. I'm going to call that name foo. The service usually has a name. I'm going to call the service foo. The ingress also has a name, and I'm going to call that ingress, let's say I call the ingress also foo. These are different resources, so they can have the same name basically. So excuse me. So the idea is that I tell the ingress that if somebody wants to access the pod which is named foo, hit the foo service. The service is told that if somebody is trying to access the service foo, then you eventually just hit the specific red color pod. If somebody is trying to hit the ingress named bar, go to the bar service, because the service is also named bar. If somebody is trying to hit bar, then you eventually reach this green color pod. So now, like, for just conceptually, we have that uniqueness architecture, such that, let's say if my instance is called foo, right? I'm telling the ingress that if somebody tries to hit foo, hit the service. If somebody tries to hit bar, hit this service. And this service knows that if somebody is hitting the bar service, just go to the green pod. This service knows that if somebody is hitting the foo service, just go to the red pod. All right. So far, conceptually, we have that. So now we just need to figure out how do we hit each of these ingresses. Now, like we said earlier, ingresses are separate units in the sense that they have their own different IP addresses. That's where the ingress controller comes in. The ingress controller is monitoring all ingresses. An ingress controller has its own singular IP address, 1.2.3.4. This is not a correct IP address, but let's say it is this, 1.2.3.4. So you go to godaddy.com, you set up a new record saying 1.2.3.4 is going to point to a wildcard domain name called *breadkv.com. What does that mean? Asterisk here refers to any name. And what you're doing in GoDaddy is saying that anybody can hit the ingress controller's IP 1.2.3.4 as long as they're hitting the domain name *breadkv.com. Let's say I hit foo.breadkv.com. Because the ingress controller has access to all of the ingresses, it knows that if somebody hits foo.breadkv.com, I need to go to an ingress called foo. And if as soon as it reaches the ingress foo, well, the ingress was earlier, like we talked about, configured. If somebody hits the ingress foo, go to the foo service, and the service knows you reach the pod. So we just solved the problem where you have a service named foo, you have an ingress named foo, the ingress controller is monitoring all ingresses, and the ingress is configured in such a way that if somebody hits foo, you hit the service. If somebody hits bar, you hit this service, and then you reach the green pod. And now we have access to a file system. Now, how is this different from the EC2 instance architecture? So if you initially think about it, each EC2 instance has had its own IP address, right? Had its own host name. And for each of those to be able to hit each of those, you would need to have a separate GoDaddy or Namecheap record in your DNS provider. And that would take hours to resolve. But here, the only address that we're actually putting into Namecheap is the ingress controllers. So 1.2.3.4 pointing to, let's say, asterisk.breadkv.com. And the ingress is configured in such a way that you say that foo.breadkv. If I get a request at foo.breadkv.com, if I get a request at the ingress named foo, basically, you go to the foo service, which gives you access to the foo pod. Now, I will slightly correct myself in the terminology and say that the ingress is actually configured to say that if I get a request at foo.breadkv.com, then I actually get to the foo service. If I get a request at bar.breadkv.com, I go to actually the bar service. So the ingress isn't configured by name. The ingress is actually configured by the incoming entire host name, which would consist of the asterisk part, and the ingress would have routing rules such that from the host name we would extract the wildcard part and we would send it to the service which is actually named the wildcard, if that makes sense. So essentially, this is what our architecture has come down to. We have an ingress controller, we have an ingress, we have a service, we have a pod. The pod is where the entire file system lives. All the files that I create from the UI, from my code base in the browser, all of that lives in the pod. How do you access the pod? Using a service. How do you access the service? Using an ingress. How do you access an ingress? The ingress is being monitored by an ingress controller, which has its IP, which you put into Namecheap GoDaddy against a wildcard domain name. And you then, on that wildcard domain name, essentially configure routing rules on the ingress such that any request that comes to, let's say, asterisk.breadkv.com, send the request to the specific service which is named asterisk, if that makes sense. So whenever I create a new instance, I create a pod that is named foo, I create a service that is, let's say, named foo, and then I create an ingress with routing rules such that if I get a request at foo.breadkv.com, send it to the service named foo. And here, I would also like to show in an example. So this is essentially, a blog I'd written about the same topic. And if you see here, if this starts responding, there we go. So we have an ingress here, which has its own name, instance name. Instance name is, let's say, foo. And what we're saying is that when we get a request at instancename.breadkv.com, I have my rules such that I send it to the specific service which is called instance name, which means that what we had here, the ingress we create for every new instance is configured with a rule such that anytime I get a request on foo.breadkv.com or bar.breadkv.com, which is the foo and bar where they are the name of the instances, we send it to this name, to the service which is actually named that instance name, which then gives us access to a pod. And if we look at the configuration for a pod, which I believe is above this, where is it? Oh yeah, it's right here. There we go. So, well, I'm not using a pod, I'm actually using a deployment, which you can think of it basically as a pod. Basically, a deployment has certain benefits that just single unit pods don't. We can forget about what volumes are, why they're useful here. Don't need to care about that. But essentially, what the main part that you need to look at is that each pod is configured with its own set of resources. So CPU, memory with certain limits for how much CPU and how much memory it can be allocated at max. And then you have a service which is actually giving us access to the specific pod, basically. And now, the real question is, how does this fit in to the entire application? How does this entire flow now suddenly work? I went to Replit.com, I said create new Java project. Sure, I created a new pod, with installed all dependencies. Let's say I installed Node, I created a new service, I created a new ingress, I created a new ingress controller. Now let's say I'm writing code. What changes? What actually happens now? What is the point of these updates? And what is basically happening under the hood now? Because now the one thing that we know is that we can access this pod, because now we have an IP address associated with foo.breadkv.com, because it's a wildcard domain. So now I know I can ping this pod. But what happens next? How do I make changes to the file system? Because again, in the UI, I'm technically making changes to files, right? I'm making changes to main.go from the browser. How do those changes get propagated here? What are the changes that actually happen? And what is actually happening on the pod level itself? And what are things that I'm actually doing here? Cool. So now to answer the question of what I'm actually doing here. So now I said UI and Next.js, and the reason I don't have an application server or a backend here is because I've assumed that you can write the backend in Next.js, which you can. I have not when I actually built this architecture like in code, I didn't actually use UI as the backend. I didn't actually use Next.js as the backend. But I've just done. I don't even know if we can satisfy all of these capabilities with an Next.js backend. But my assumption is we can, and I just didn't want to add one more box here. But we're just going to assume that this is the backend, basically, the UI and the backend, basically. So when I go on create instance, right, I say let's say create Java project. I would create a pod, let's say called foo, create a service called foo, create an ingress with a routing rule saying that if I get a request at foo.breadkv.com, send it to the foo service, which gives access to the pod. Now, in the UI, I see a main.go file, or let's say, sorry, TypeScript file. Let's say I see a, don't even know, main.ts file, right? Let's say I wrote a bunch of commands. I wrote a bunch of code in the code base editor itself, for example. How do those changes actually get propagated? Now, if you think about it from first principles, this pod this pod actually consists of a file system. And excuse me, by the way. So this pod actually consists of a file system, and that file system consists of a main.go file, of the other files that I would potentially create. Now, this backend server, we know, needs to communicate with the pod to actually make changes to the file system. So ideally, we need something running on this pod that I can communicate with, so that it can actually make changes on the file system itself. And this is where we would actually run a WebSocket server on the pod itself. Now, a WebSocket server is basically this real-time server, which can communicate with clients in real time, and it can take in events, and on the basis of those events, perform actions on the pod itself. So what we would do is that whenever the pod starts and the service and the ingress and everything is created, we actually run a WebSocket server on the pod itself, which would be listening to events. And my backend actually creates a WebSocket connection, or actually rather my front end actually creates a WebSocket connection with this specific pod itself, if that makes sense. So what we now actually do is that, let's say I'm in the code base in the UI, and in my main.go file, I write package main. Those file system edits are now, because now I have a WebSocket connection here, those where I can actually send that change event from the UI to the pod itself, because now I would be hitting the server name foo.breadkv.com, which is associated with the ingress controller, which monitors ingresses, and the ingress knows that if I get a request at foo.breadkv.com, I need to go to the service foo, which gives access to the pod. And the WebSocket server that is actually running on the pod would receive the change file event, and it will also receive a payload with what file needs to be changed, and the content that needs to be edited, and it would actually edit it on the pod itself. Now, there are some complications around how frequently you edit it on the file system. Do you only change diffs, or do you actually change everything? And that's a fairly complicated problem to solve. And the solution to that is that you only change diffs, because let's say you have like a 500 line 5000 line file, for instance, right? Like, let's just say you have a 5000 line file, which is ridiculously large. Now in that case, you obviously, if you change one line, you don't want to overwrite the entire file on the pod, because that consumes a lot of overhead from a resources standpoint. So you only want to manage diffs, and that brings its own level of complications, essentially. But the fundamental idea is that whenever you start the pod, you actually also start a WebSocket server which your client can actually connect to, so that whenever you make a change on the UI side of things, you actually emit that WebSocket event to the pod itself, to foo.breadkv.com, which eventually through this entire architecture reaches the pod. And the pod is where you actually end up making all the edits, and you end up doing a bunch of that stuff basically. And this is essentially what the final architecture is, like I talked about, where the ingress controller is what goes on Namecheap, GoDaddy, and all of these other constructs can just be created via a Kubernetes SDK, written in Go, Java, Python, whatever language you prefer. Kubernetes has an SDK that's offered for a bunch of these common languages. And yeah, I mean, that's that generally. And if I were to quickly show you some code, extremely ugly looking code. So, if this is just some extremely ugly looking code, so if you see here, this is actually the runner for what's actually running on the WebSocket server on the pod itself. This is the WebSocket server running on the pod. And we see here that if parse data.type, parse data is actually what the payload that is actually received from the client itself. And it says that if it says update file, you create a write to file function, and this is actually all being written on the pod itself, on the specific user's pod itself. If I'm able to zoom out a little bit, which I'm not able to. Okay, I guess I'm not able to zoom out, but basically that's that. And you're able to write the file, and essentially you're writing to the actual file system. And now, just a very quick summary on what we solved for. So the goal is that every user needs to be able to get their own instance, right? And a couple of problems are, one, you want instances to be provisioned quickly. Pods and services and all of those can actually be provisioned fairly quickly. And they can happen within a minute, and as long as installing dependencies doesn't take too much time. So for example, if you're running, I don't know, a Go project, like that should be fine. But like if you're running something complex, it might take a little bit longer to install all dependencies, but it can happen in a fairly quick amount of time. There is no DNS resolution on the fly happening. And also the important thing about certificates, right? So the important part about certificates is that about HTTP, HTTPS, is that you can access everything within Kubernetes on HTTPS, because now you can actually, if you see the ingress controller, which has its own IP, which you were assigning wildcard domains to, there is a way to be able to assign certificates and to get past SSL TLS errors by creating certificates for wildcard domains in Kubernetes. It is possible. I have done it, and you can do it as well. And therefore that takes away the whole DNS resolution problem too. And this limit brings us to like extremely simple YAML configurations that you just need to write. If you want to allocate more resources, just have that YAML configuration that needs to be edited, which I'm sure can be done via the SDK. And if you want to, let's say, provision instances for more, or if you want to open more ports, again, that can be done via the SDK, which is a great solution to have. And this is like a really quick example of what I had built using the exact same architecture, which was a key value database in the browser, where you can run your own instance of like a Redis like database or whatever. And if you quickly go and watch the demo, it's an extremely ugly demo. And the only reason I don't have it running right now is because I what do you call it? It was costing me a lot of money to run a Kubernetes cluster with a bunch of resources provisioned. It wasn't costing me a lot of money, but it was costing me enough money to get me broke, because I'm a student. So if you see here, like when I click on start, I'm now provisioning my own instance. It's not clear at all, but there is an instance ID here. And this ID is actually what's going to be the name of the pod, the service, the ingress, the ingress.breadkv.com, or whatever, which has routing rules defined to go to the specific service. And if you see here, I eventually have my own instance created. and you can run a bunch of commands, and all of these commands are being executed on your specific instance itself. And you know, here it's not visible, but I ran a command called ping Anish, and it returns back Anish because this command is being executed on that instance itself. And there are, if we go back, there's also a bunch of like random docs on these, which hopefully they open. I freaked out. I thought I was having issues, but yeah, there are basically a bunch of docs for how this was built. Mainly the Kubernetes constructs on how this was built, with a bunch of examples for what's actually happening under the hood. But yeah, and essentially that was that, and that was all about the architecture for how you can build something where you need to provision your own instances for different users. And I will now go and figure out what I want to talk about next.